Hello, it's Dr. Harris again with further videos, another video for our Chapter 7 out of our Statistics Math 111 course. In the last video, we looked at sampling distribution for the sample mean. So we looked at uh, what shape uh, the statistic X bar takes on over repeated sampling for a given sample size. And we found that it's bell-shaped with standard deviation, population standard deviation sigma over the square root of the sample size. But at the end of that video, we mentioned that since we don't know the population standard deviation sigma, we will replace it with the sample standard deviation S, but that doing so to use S over the square root of n as our standard error uh, introduced a small problem in that uh, the distribution of X bar under that assumption is no longer normal. It's still bell-shaped, but it's a little bit more spread out. And so in this slideshow, we're going to start off by talking about what that new distribution is, and then we will work some examples involving confidence intervals where we use this new distribution. And so these distributions are called T distributions. So let's go ahead and get started on that. So as I mentioned before, back in chapters 5 and 6, our statistics p hat and p1 hat minus p2 hat were pretty close to normal even when we used our approximation for the standard error. And so we could use p norm gc in finding p-values in our hypothesis tests. And we would use the multiplier z star, which was based on normal distribution for confidence intervals. We're not going to be able to do that now because S over the square root of n is not going to have a normal distribution. And the distribution it does have is called a T distribution. And T distributions are, as I mentioned, bell-shaped, but they're more spread out. They have a not quite as high peak as normal distributions do, and they also have what we might call fatter tails. They're thicker on the ends. They're just more spread out. And so one implication of that, as I say here, is that the percentage of times that a T distribution will take on a value between -1 and 1 is going to be a little bit less than 68%. Here, a value of T being basically a T-score, how many standard errors the observation is away from the center. And so our T distributions are going to be centered at 0. So in the 68-95 rule for normal distributions, we said 68% of observations were within one standard deviation of the mean. Here for T distributions, a little bit less than 68% of observations will be within one standard error of the mean. Likewise, a little bit less than 95% of observations will be within two standard errors of the mean. And this last sentence here on the slide just attempts to give a brief explanation as to why T distributions are more spread out. And that's because since we're using the sample standard deviation S, there's going to be a lot of variety, a lot of variability in what the standard error might be, because since we have different samples, we'll have different sample standard deviations. And so what winds up happening is that variance in the value of S, the variation in the value of S, causes the distribution of X bar to be a little bit more spread out than it would be if it were truly normal. But there's one other thing to mention about T distributions, is that there actually is a collection of T distributions. It's not just a single distribution, like a normal distribution centered at 0. There are infinitely many T distributions centered at 0. And there's a different one for each different sample size. So if I conducted an experiment where the sample size was 25 and then another experiment where the sample size was 40, I would be expecting the distribution of my data to have slightly different characteristics based on the sample size. And so associated with each T distribution is a number we call the degrees of freedom. And we've encountered that term before I'll explain it in a couple of slides, what we're doing with degrees of freedom here. But the bottom line is that the number of degrees of freedom with a t-distribution is 1 less than the sample size. So if our sample size is n, we will have n minus 1 degrees of freedom on our t-distribution. So if I conducted an experiment with a sample size of 15, the corresponding t-distribution would have 14 degrees of freedom. If instead I had a sample size 28, I'd have 27 degrees of freedom. We've got a question here at the bottom. What would the sample size be if the t-distribution had 44 degrees of freedom? I'll give you 5 seconds to think about that, and I'll give you the answer. So if we're given the degrees of freedom, that means the sample size is going to be 1 more than that number. And so with 44 degrees of freedom, our sample size would have been 45. So I'm not going to take you there, but if you look at page 253 in your text, you'll see a couple of graphics that illustrate how t-distributions relate to normal distributions. The top figure, I think, clearly indicates that a t-distribution has a shorter peak and fatter tails than a normal distribution does. But the second figure at the bottom, toward the bottom of the page, tries to illustrate what happens as the number of degrees of freedom gets bigger. And hopefully what you can tell is that as the number of degrees of freedom increase, the t-distribution gets a little bit higher, the tails get a little less fat, and so the closer to a normal distribution we get. So as n increases, our t-distribution does look more like a normal distribution, but we're still not going to say that it does have a normal distribution. So let's briefly talk about what degrees of freedom means in this case. In chapter 6, when we were talking about the chi-square distribution, when we were testing for independence between two categorical variables, it referred to the number of free choices that we had to fill out a table, given that we had row totals and column totals. It's sort of analogous here. What we're fixing in advance is the value of the standard deviation. And if you do that, if you say, I've got a sample that has a particular standard deviation, once you choose all but one of the numbers in the data set, the last one is automatically determined in order to get the specific value of the standard deviation that you have. So what the free choices we have here are the number of free choices in deciding what our data set looks like given a standard deviation value. And so it's always 1 less than the sample size. So that's what we're going to be working with here for degrees of freedom. We are going to use t-scores a fair amount in this chapter. So remember what a z-score was. It was measured the number of standard deviations an observation was either above or below the mean. There's an analogous meaning here for t-scores. A t-score for a given sample mean is going to be the sample mean minus the population mean divided by the standard error. And so it's measuring how many standard errors an observation is above or below the mean. So we'll be using this when we work with hypothesis tests in the next slideshow, but we will do a little bit with t-scores right now. And the command that helps us calculate probabilities underneath t-distributions is called ptgc, and it functions in a way similar to that of pnorm GC, although there are going to be a couple of differences. We'll see. So let's look at how ptgc works. So the thing we do is we have to supply the number of degrees of freedom. We don't have to supply a mean and standard deviation like we did with pnorm GC because we'll always be assuming that the mean of a t-distribution is 0. And so we just give it the t-score. If we want, as I say here in this example, we'll give it a t-score, a range, a number of degrees of freedom, and then graph equals true will help us visualize what we have on hand. So if I wanted to find the probability that a t-score that came from a sample of size 20 was bigger than 1.15, I could use ptgc as follows. ptgc of 1.15 If I want it to be more than 1.15, I'll use region equals above. With a sample of size 20, our degrees of freedom is 19. And so if I enter this command into our studio, I'll get a graphic that looks like this. And we discover that a little bit more than 13% of the time, with a t-distribution with 19 degrees of freedom, our t-score would be above 1.15. So again, PTGC is going to be one of our new commands that we're introducing in this chapter. It's going to calculate areas under curves when we've got t-distributions. And so it'll help us with p-values, probabilities, and so on. Another example real quickly, what's the probability that a t-score is more than 1.84 in absolute value given a sample size of 34? So we need the number of degrees of freedom, that's 33 in this case. And just a reminder, when we talk about something being more than a number in absolute value, we're talking about being greater than that number or less than the opposite of that number. And so here, if I want a number to be 1.84 in absolute value or more, that means it's going to be either more than 1.84 or less than negative 1.84. And so this is an example where we are using an outside region. We're asking what's the probability that a t-score is either bigger than 1.84 or less than negative 1.84. So our region set to outside, we have 33 degrees of freedom, and our graphic when we enter the command is this. And so this is the range outside negative 1.84 to 1.84, and it turns out it's about a 7.5% chance that a t-score would be 1.84 or farther away from zero on either side. And hopefully you can see that this is akin to the types of things we were doing with p-values back in chapters 5 and 6. So we will do a little bit more with PTGC here to help us think about how things are going to be a little bit different when we're dealing with confidence intervals. So you've got a simple random sample of size 40. You don't know the mean or standard deviation, but let's ask, what's the probability that the t-score would be between negative 1.96 and 1.96? Well, as long as we know the sample size, we know the number of degrees of freedom, and so we can calculate the area between negative 1.96 and 1.96 underneath a t-distribution with that many degrees of freedom. So why am I doing 1.96 here? Well, you want to recall that that was the multiplier that we used in confidence intervals when we had a normal distribution. That 95% of the time, a sample proportion would be within 1.96 standard errors of the population proportion. And so we're wanting to see, could we use 1.96 as a multiplier for 95% confidence intervals with sample means? And the answer is that if the sample size is big enough, we're not too far off. We can see here that since the area between negative 1.96 and 1.96 with 39 degrees of freedom is 0.943, rounded to three decimal places, what we would be computing if we use 1.96 as a multiplier is not a 95% confidence interval, but a 94.3% confidence interval. So not too far off, but still not quite the same. Okay, this is again an effect of t-distributions being more spread out. There's not 95% of the area underneath the curve between negative 1.96 and 1.96 like it was underneath the normal curve. So nonetheless, if the sample size were 40, a 94.3% confidence interval isn't that far off from a 95% confidence interval. We're not going to do that with such a large sample size, but we want to recognize that it's not terrible. However, if we had a much smaller sample size, say sample size 8, with 7 degrees of freedom, we would not be computing anything remotely close to a 95% confidence interval. It looks like we would be computing about a 91% confidence interval. And so we shouldn't be using t-star 1.96 for our multiplier for confidence intervals with sample means, because we're not going to get quite 95% confidence. So what are we going to do instead? Well, we're going to talk about that in the next slide. Clearly, we're going to need to do something. And we're going to say goodbye to PTGC for now. That will come up in our next slideshow when we start talking about p-values for hypothesis tests. So now what are we going to do to compute confidence intervals? Well, we're not going to use z-star, but we're going to use a value called t-star. And so as I say here, it's still going to be capturing a middle percentage of a t-distribution, but the values of t-star are going to be a little bit bigger. We have to go a little bit farther out on t-distributions in order to capture the middle 95%, or the middle 90%, or the middle 99%. So the endpoints for a confidence interval for a population mean are going to look similar in style to what we've seen before. We've got a statistic plus or minus a multiplier times a standard error, but our standard error this time is s over the square root of n, and our multiplier is now going to be a number called t-star. And our t-star values are going to be a little bit bigger than the z-star values that we saw before. How are we going to find these multipliers? Well, we're going to be using a table that's in the back of our textbook. And so it's on pages 414 and 415. And so I'm going to be going there in just a minute to show you what to do. But let's read through what my described process is for this. So before we go to the table, we're going to need to know how many degrees of freedom we have, and we're going to need to know what our confidence level is. So it'll be either 90%, 95%, or 99%, but we'll also need to know our degrees of freedom. So our table is going to have, we're going to have to find the right row and the right column. And so we'll find the right row by looking at the degrees of freedom heading for that row. And we'll identify the right column by knowing what our confidence level is and corresponding that to a two-tail area. So as I say here, for 90% confidence intervals, we'll use a two-tail area of 0.1, 95%, a two-tail area of 0.05, a 99% confidence, we'll use a two-tail area of 0.01. And the value of t-star that we want is going to be the intersection of the row and column. So let's look at an example, and then I'll switch over to the table in the text to look through this. If our degrees of freedom were 28 and we wanted to compute a 95% confidence interval, what would we use for t-star? Well, here's the table from page 414. And if I scroll down, I'm looking for 28 degrees of freedom. So that's this row right here. So my row heading is the degrees of freedom. And if I want a 95% confidence interval, my two-tail area is going to be 5%. So we compute our tail area by subtracting our confidence level from 100% and converting it to a decimal. So 100% minus 95% is 5%. 5% written as a decimal is 0.05. And so the column heading is this third one here, 0.05. So for 28 degrees of freedom and 95% confidence interval, two-tail area 0.05, it looks like our t-star value is going to be 2.05. We expected it to be bigger than 1.96, and so it is a little bit bigger than 1.96. It's 2.05. What's our second question? If we had 11 degrees of freedom and a 90% confidence interval, what value of t-star would we use? Well, we go to the 11 degrees of freedom row here, and our two-tail area this time is going to be 0.1. 100% minus 90% is 10%. 10% as a decimal is 0.1. And so we're going to use the second column this time, 11 degrees of freedom. Our t-star value is 1.8. And there are our answers. And as I pointed out, we expected t-star to be bigger because the t-distributions are farther spread out. Okay, so last thing before we actually start computing confidence intervals, remember back in chapters 5 and 6, we had conditions that needed to be met before we could use these formulas. There it was independent selections and success failure condition. Here, again, we have to be able to tell that our sample is randomly selected, i.e. representative of the population. But the other thing we have to do is we have to be able to convince ourselves that the distribution of the population is at least somewhat bell-shaped, especially if the sample size is pretty small. So, as always, we talked about this at the beginning of the course. we generally want to make a graph of somehow of our sample. That's all we're going to have to go on. We're going to have to use the sample as a proxy for the population. So we can do a density plot, a histogram, something from our sample to see whether or not it's bell-shaped. If the sample is, say, less than 30, we really need to look carefully for skewness outliers. We need to be able to make a case that it seems like the population would be could reasonably be assumed to be bell-shaped in nature. And as I say here, the smaller the sample size, the more that skew or outliers should make us concerned about whether or not this is the right course of action to be taking. But let's look at an example now. So we've talked about conditions. We've got our formula for confidence intervals. Let's actually work through an example where we find a confidence interval. And let's go to page 261 in our textbook. Let's read problem 7.11. Georgiana claims that in a small city renowned for its music school, the average child, and I'm saying strike the words less than, takes 5 years of piano lessons. So we're not going to worry about the words less than here, just ignore them. We take a random sample of 20 children from the city, and we find that they have a mean of 4.6 years of piano lessons and a standard deviation of 2.2. We're only going to look at part B in this video and slideshow. We'll come back and look at parts A and C in the next slideshow. But part B says construct a 95% confidence interval for the number of years students in the city take piano lessons and interpret it in context of the data. So we're told that the sample mean, x bar, is 4.6, and our sample standard deviation, S, is 2.2. Okay, so let's take a look at this. We've gotten some practice already on describing what the parameter of interest is. It's a population mean. It's the mean number of years of piano lessons that children in this town have taken. And so I've got that written here. Our sample size is 20. That's pretty small. And the question that we should always want to ask ourselves is, should we even bother to proceed? And this is one of those cases where we actually weren't given any access to what the data looks like, how symmetric or skewed it is. We have nothing. And so we generally should not do this if we can at all possible avoid it, but we can't avoid it here. We're just going to have to assume that there's no big skew, there are no big outliers in our data. We have to assume that things are okay to proceed. So even though we don't have sufficient information to be confident about proceeding, we're going to go ahead and do so anyway. But we maybe in our write-up should note that we were proceeding with a certain level of trust here. So how many degrees of freedom do we have? Well, our sample size was 20, and so our degrees of freedom is going to be 19. What's our two-tail area? Well, if we're looking for a 95% confidence interval, our two-tail area is going to be 0.05. And so what's our value of T star? Well, we can go back to the book and check that out. So back to page 414 with 19 degrees of freedom and a 95% confidence interval, our T star value is going to be 2.09. So T star 2.09. So we know that X bar was 4.6, S was 2.2, N is 20, T star is 2.09. And so we can put that all together. The low end point of our confidence interval is going to be the sample mean, 4.6, minus our multiplier, 2.09, times the sample standard deviation, S, divided by the square root of the sample size, 2.2 over the square root of 20. If you do the arithmetic and round it to 2 decimal places, you get 3.57. And then you add 2.09 times 2.2 over the square root of 20 to 4.6, you get 5.63, excuse me. So we are 95% confident that the mean number of years of piano lessons obtained by children in the city is somewhere between 3.57 and 5.63 hours. Okay, so we want to write down all the information that we were given, make sure we label all our values properly, substitute them properly into our formula. So I'm going to end here by asking you to do a couple things that we can talk about in class. What would we do differently if we had a 99% confidence interval? And I'll ask you to work that out, and we'll talk about that in class. And then lastly, here's another example. This is from the very first day of class, our very first slideshow. Here's an example. A city builds a public parking garage downtown. They are going to pay for the cost of construction with parking fees. The consultant told them that they should expect to collect $126 on average in parking fees during weekdays. They do obtain $126. The consultant, we're going to come back and talk about the consultant in the hypothesis test in the next slideshow. But if our average was $126 per day with a standard deviation of $20, let's find a confidence interval. So I want you to find 90% and 95% confidence intervals for our population mean, but not before you describe the population mean in words. So this is practice for you. So please do this. We'll get together and go over the answers when we get together in class.